There is something deeply unsettling about the way Interstellar begins. Humanity is not wiped out by war or fire or some sudden cosmic catastrophe. It is being quietly starved by a dying world. Then, almost impossibly, a door appears near Saturn, not a machine, not an explosion, but a distortion in reality itself. A tunnel through space-time, hanging there as if the universe has bent inward and left us an opening. The film asks you to accept that this is how our last chance arrives. But before we can decide whether that hope is real, we have to confront a stranger question. What would it actually mean for such a thing to exist at all? At first glance, the wormhole in Interstellar feels like one of the film's boldest inventions. It is the sort of idea science fiction has trained us to recognize immediately. A shortcut across impossible distances, a bridge between where we are and where we could never otherwise reach. Yet one of the most impressive things about the film is that it does not present the wormhole as a glowing doorway or a neat circular gate cut into empty space. It shows something far more disturbing and far more credible. The stars behind it appear warped. Light bends around its edge. Space itself seems to have lost its usual order. That is an important place to begin, because if a wormhole were ever visible, this is more or less how we would expect it to reveal itself. Not as an object in the ordinary sense, but as a region where geometry becomes strange enough to manipulate light. In everyday life, we think of space as empty background, a silent stage on which matter moves around. General relativity changed that picture forever. It told us that space and time are not passive, they are part of the drama. Matter and energy shape space-time, and space-time tells matter how to move. Gravity, in that view, is not really a force pulling things across emptiness. It is the curve of the stage itself. Black holes are the most famous example of that idea taken to an extreme. A wormhole belongs to the same family of thought. It is another severe distortion of space-time, another solution that can emerge from Einstein's equations when gravity becomes powerful enough and geometry becomes flexible enough. In the simplest terms, a wormhole is a shortcut. Two regions that would normally be separated by a huge distance are connected through a shorter path that cuts through curved space-time. The classic analogy is a sheet of paper. If one point lies on one side and another far away on the other, the long route stays on the surface. But if the paper is folded so those 2 points touch, a pencil could punch straight through and create a shortcut. It is a useful analogy, even if the real thing is far stranger. Because in reality, we are not talking about a sheet being folded inside some higher room. We are talking about space-time itself, being arranged in a way that allows distant locations to become neighbours through a hidden path. Interstellar uses this idea carefully. It understands that the wormhole is not just a storytelling device. It is the first major scientific test in the film. If the wormhole looks ridiculous, the rest begins to collapse. If it feels grounded, even tentatively, then the audience is willing to follow the story deeper into its more dangerous claims. And in one sense, the film earns that trust. Wormholes are not pure fantasy in the way a magic portal would be. Physics really does contain the mathematical language to describe them. The possibility exists inside the theory. That distinction matters, but it matters just as much to understand what that statement does not mean. A mathematical solution is not the same thing as a physical object we know can form in nature. The history of physics is full of equations that permit strange structures without proving that the universe actually builds them. The wormhole lives in that uneasy space between elegant mathematics and unproven reality. That is where the trouble begins. The first problem is creation. Even if space-time can in principle be arranged into a wormhole, how would such a structure ever come into being? We do not know. More than that, some lines of reasoning suggest the very act of making one may drag us into territory the universe refuses to allow. Once you imagine two linked mouths of a wormhole existing at once, another possibility appears almost immediately. If one end experiences time differently from the other, then travelling through the wormhole may no longer be just travel through space. It may become travel through time. Picture the situation carefully. Suppose two mouths are linked. Then imagine moving one of them in such a way that it undergoes strong time dilation and ages more slowly than the other. Perhaps it is accelerated to enormous speeds or placed in a stronger gravitational field. When the two mouths are brought back into some useful arrangement, they remain linked but no longer share the same passage of time. Entering one mouth could mean emerging not just elsewhere, but earlier. The shortcut becomes a route into the past. Now the idea stops being merely exotic and starts becoming corrosive. Because once travel into the past enters the picture, paradox follows close behind. You could, in principle, interfere with the very chain of events that allowed your journey to happen. You could prevent your earlier self from entering the wormhole. You could block the creation of the mission. You could tamper with causes using effects that have not happened yet. This is where wormholes collide with one of the deepest discomforts in physics. Not just that they are strange, but that they seem to invite logical loops that reality may not be able to sustain. Some physicists have argued that the laws of nature likely protect causality from this kind of breakdown. The idea is often captured in a simple intuition. The universe may permit many bizarre things, but it may forbid anything that allows history to contradict itself. That possibility does not amount to a proof. We do not possess a final theorem declaring wormholes impossible, but the presence of these causal loops is one reason many physicists remain skeptical that such structures could ever be more than formal solutions on paper. Interstellar does not dwell on that skepticism for long, but it quietly depends on the audience not pushing too hard on the question. Because if wormholes naturally lead toward time travel, then the film's central hope is already tied to a deeper instability. And even if we set paradox aside, there is a second problem that may be even more immediate. A wormhole might not stay open long enough for anyone to use it. This is one of the most important ideas in the whole discussion, because it pushes the wormhole from speculative concept into practical impossibility. In many models, the throat of a wormhole is not stable. Gravity works against it. The curvature tends to collapse inward. The tunnel pinches shut. So even if a wormhole could somehow appear, it might close the moment anything tried to pass through it. Cooper's mission would be over before it began. The bridge would seal itself under its own gravitational logic. To get around this, physicists are forced into a deeply uncomfortable move. They introduce something exotic at the throat of the wormhole, something with negative energy density, or effectively negative mass. Ordinary matter attracts. This hypothetical material would do the opposite in just the right way. It would create the opposing curvature needed to keep the tunnel from collapsing. In effect, it would prop the wormhole open against gravity's urge to close it. This is where the science becomes simultaneously rigorous and fragile. Rigorous because the mathematics describing the need for such support is not arbitrary. Fragile because the support itself is something we do not know how to obtain in the required form. Negative mass is not part of ordinary experience. It has never been found as a usable material. We have no engineering path to gathering it, shaping it, and holding a traversable wormhole open with it. So the wormhole remains a kind of conditional truth. If exotic matter exists in the right way, and if it can be arranged in the right geometry, and if the universe tolerates the causal consequences, then perhaps a stable passage might be possible. But you can feel how many doors have to remain open at once. That, in many ways, is what Interstellar does so well. It does not build its journey on something that is plainly impossible under known physics. It builds it on something perched right at the boundary, allowed by equations, unsupported by evidence, seductively close to science, and still beyond our grasp. There is another reason the wormhole in the film works so effectively, and it has less to do with pure theory than with visual honesty. The film understands that once space-time is distorted, light itself becomes part of the story. You would not simply look at a wormhole. You would look through a region where the paths of photons have been bent into strange curves. Background stars would no longer sit where your intuition expects them. Images would smear, twist, and wrap around the geometry doing the bending. In that sense, the film makes a smart choice. It grounds wonder in optics. It lets gravitational distortion create the spectacle, rather than painting spectacle on top of empty physics. This matters because visual credibility carries emotional credibility. When we see the stars deform around the wormhole, we do not just see an effect. We see the idea that space-time is real enough to behave like a substance with structure. And once that belief takes hold, the rest of the story can begin to ask much more dangerous questions. If space can fold, can time slip? If distance can be cheated, can causality be bruised? If our salvation depends on a tunnel that should not naturally exist, then perhaps the rescue already contains the seed of the film's greatest problem. Because the wormhole is not merely transportation. It is the first sign that the universe in Interstellar may already be caught inside a loop. A shortcut through space-time is one thing, a shortcut through cause and effect is another. And once those two possibilities begin to overlap, the mission to save humanity no longer rests on engineering alone. It rests on whether reality itself can survive the kind of geometry the film is asking us to enter. The crew, of course, goes through anyway. That is what the story demands. Without the wormhole, there is no system beyond Saturn, no Gargantua, no Miller's planet, no later revelation waiting in the darkness. But the price of accepting that passage is accepting that the film has quietly planted a paradox at the foundation of everything that follows. The tunnel may be visible, the equations may gesture toward it, the imagery may feel uncannily right, yet the closer you look, the less it resembles a doorway, and the more it resembles a stress fracture in the logic of the universe. And once you have crossed a fracture like that, the next question is no longer whether the journey is possible. It is what kind of place would have to exist on the far side to make all of this seem almost reasonable. A place dominated by an object so extreme that it can slow time, shape worlds, and drag every hopeful idea in the film toward the edge of an event horizon. That event horizon is where Interstellar begins to tighten its grip on time, causality, and the cost of using a shortcut that physics may never truly allow. Because even before Gargantua takes over the story, the wormhole has already forced us into a more uncomfortable line of thought. It is one thing to imagine a tunnel joining two distant places. It is another to ask what happens if the two ends of that tunnel stop agreeing about when they are. This is where the wormhole idea stops being merely geometric and starts becoming temporal. If two mouths of a wormhole remain connected internally, while one of them experiences time more slowly, they can drift out of sync. From the outside, they still appear to be two entrances to the same structure, but they no longer belong to the same moment in time. Travel through the shortcut could then produce a result that ordinary travel never could. You do not just arrive somewhere else, you arrive else when. The basic mechanism behind that possibility is not invented for science fiction. It grows directly out of special relativity and general relativity. Time does not flow identically for all observers. It stretches and compresses, depending on motion and gravity. A fast-moving clock ticks more slowly relative to a stationary one. A clock deeper in a gravitational field also runs more slowly than one farther away. These effects are tiny in ordinary life, but they are real. They have been measured. Satellites, atomic clocks, and precision experiments all confirm that time is not the fixed universal background we once imagined. Now apply that to a wormhole with two mouths. Suppose one mouth stays relatively still, while the other undergoes a journey involving enormous velocity, or spends time in an intense gravitational field before being moved back. The two mouths remain part of the same wormhole structure, but from the outside, they have aged differently. Their internal connection has not obeyed the same external passage of time, and that means a traveller entering one side could emerge at a time earlier than the time of entry, according to the outside universe. At that point, the phrase time machine stops sounding metaphorical. This is not a minor side effect. It is one of the most serious conceptual consequences of traversable wormholes, and it changes the entire emotional weight of the film's premise. The mission in Interstellar feels like a desperate expedition outward. But if the geometry enabling that expedition also permits backward time travel under the right conditions, then the story is no longer just about distance, survival, and exploration. It is about causality under stress. The film can keep that implication in the background, but physics does not let it vanish so easily. Why does this matter so much? Because causality is one of the deepest organizing principles in science. Causes precede effects. Events follow coherent chains. Our equations, experiments, and explanations all depend on the assumption that the universe has some meaningful order in time. If that order can be violated, then logic itself becomes vulnerable. A message can be sent before it is created. A machine can be built using instructions that came from its own future. A person can interfere with the conditions that led to their own action. The result is not merely weird, it is destabilizing. The best known version is the grandfather paradox. If someone travels into the past and prevents the circumstances that led to their own journey, then their trip seems to erase its own cause. But wormholes invite subtler versions too. A scientist could receive a formula through a wormhole, publish it, and years later send that same formula back through the wormhole to their younger self. The information exists, but it has no clear origin. It is trapped in a loop. In a universe that allows such loops, the question is no longer just what happened, it is where the happening came from in the first place. There are ways physicists have tried to soften this problem. One idea is that consistency somehow enforces itself. In that picture, events inside a causal loop can occur, but only in ways that do not generate contradiction. You can go into the past, but you cannot alter it in a way that breaks the very history that allowed you to go there. The loop closes on itself without tearing logic apart. This is elegant in one sense, but unsettling in another. It replaces contradiction with inevitability. Instead of history being broken, history becomes locked. Another possibility is more severe. Perhaps the universe simply never lets conditions mature to the point where these loops become physically usable. Perhaps quantum effects destabilize the wormhole before paradox can emerge. Perhaps energy builds up catastrophically near the threshold of causality violation and destroys the passage. In this view, wormholes are not outlawed at the level of pure mathematics, but the real universe censors them the moment they threaten temporal order. That idea has appealed to many physicists because it preserves the possibility of strange geometries while still protecting the broader coherence of reality. And that brings us to a subtle but important point about Interstellar. The film's wormhole is not merely a speculative tunnel. It is a speculative tunnel that is positioned within a story increasingly concerned with time. Once we know where the film is headed, it becomes impossible not to notice the deeper pattern. The wormhole is the first piece of machinery in a universe where time will later bend, fold, and eventually become something almost navigable. So even in these early moments, the wormhole is carrying more narrative weight than simple transportation. It is the first warning that time itself is about to stop behaving like a one-way road. Still, paradox is not the only challenge. Even if we generously imagine a universe that can tolerate causal weirdness without collapsing into contradiction, the traveller still has to get through the wormhole alive. And here the idea becomes brutally physical again. A traversable wormhole is not just a mathematical handle connecting two coordinates. It would have structure. It would have a throat, a region of extreme curvature where space-time narrows and turns inward. The geometry there is not passive. It has to resist collapse while matter passes through it. If that resistance fails for even a moment, the shortcut closes. Any traveller inside would not complete a journey. They would be caught in the failure of the passage itself. Under ordinary gravity, collapse is the natural tendency. Positive energy density bends space-time in the familiar, attractive direction. A wormhole throat, held open against that tendency, needs something profoundly non-ordinary. This is why exotic matter enters the story. It is not decorative speculation. It is a structural necessity in most traversable models. Without some form of negative energy density, the throat pinches shut. The geometry falls inward. The wormhole becomes non-traversable or never usable in the first place. Negative energy sounds like science fiction language, but it emerges from real theoretical discussion. Certain quantum effects hint that nature can produce small, local regions where energy conditions, at least in a limited sense, appear violated. The Casimir effect is often mentioned in this context, where quantum fields between closely spaced surfaces can create measurable forces associated with altered vacuum energy. But this is a very long way from saying we can collect macroscopic negative energy, store it, and build an interstellar tunnel braced against collapse. The gap between those ideas is vast. And that gap matters, because the wormhole in Interstellar is not a microscopic fluctuation. It is large enough for a spacecraft to cross. It is stable enough to remain in place. It is quiet enough to behave like infrastructure. That is an extraordinary demand. Even if quantum theory allows hints of exotic energy under special conditions, scaling that into an engineered, traversable wormhole requires assumptions stacked on top of assumptions. We need the right material. We need enough of it. We need a way to arrange it precisely. We need the structure not to decay, explode, evaporate, or destabilize when ordinary matter enters. Physics has not shown us a path to any of that. This is why wormholes occupy such a fascinating middle ground in science. They are not nonsense. They are not forbidden with the clean certainty of a square circle. But neither are they on the near horizon of technology, or even on a clear path from known laws to known construction. They exist, in theory, as permission without method, a kind of formal maybe. The equations open the door a crack, then reality stands there asking whether we have mistaken mathematical elegance for physical possibility. Interstellar benefits enormously from living inside that uncertainty. Had the film relied on an ordinary fantasy portal, its scientific ambitions would have felt thinner. By grounding its shortcut in an idea real physicists have actually explored, it gains legitimacy. Yet the legitimacy is conditional. The wormhole is scientifically literate, not scientifically secured. That distinction is easy to miss when the film's imagery is so convincing. And the imagery really is crucial. A realistic wormhole would not present itself as a flat window cut into space. A flat circular image is merely what human intuition wants to see. But the geometry of a wormhole would bend light from all directions. Depending on how the throat and mouths are shaped, the surrounding star field could wrap, distort, duplicate, or appear to come from unexpected angles. What seems like an opening might contain visual information from regions behind, around, or effectively through the curved space-time itself. The film takes this seriously enough to avoid the most obvious visual clichés, and that alone helps anchor the audience in the feeling that this is gravity, not magic. But there is another side to that visual realism. It reminds us that crossing a wormhole would not be psychologically simple, even if it were physically possible. A traveller would move through a region where the normal mapping between sight and space breaks down. Forward, behind, above, and around might no longer behave in familiar ways. Orientation would become strange. Light itself would testify that geometry had become hostile to intuition. The journey would not feel like passing through a tunnel in the ordinary sense. It would feel like entering a place where the structure of reality had been rewritten. That is why the wormhole in Interstellar feels so powerful. It is not just beautiful, it is conceptually invasive. It forces the viewer to accept that space-time might be shaped into forms the human mind does not naturally grasp, and that the price of using those forms may not simply be fuel, courage, or engineering. The price may be causality, stability, and the right to trust time as a clean sequence of before and after. By the time the Endurance crew passes through the wormhole, the film has already asked for an enormous suspension of certainty. It has asked us to believe that a traversable wormhole can exist, that it can remain open, that its geometry can be survived, and that the causal risks bound up in its existence have somehow been contained. That is a tremendous stack of assumptions, yet strangely, the film carries them well, because it knows not to rush past the weight of the idea. It lingers on the distortion. It makes the passage feel solemn, almost sacred, as though the crew is not simply travelling, but trespassing. And when they emerge on the far side, the story becomes even more precarious. A wormhole capable of bringing them here is already an extraordinary violation of normal expectations. But what waits beyond is anchored by something even more extreme than the tunnel itself. Not merely a distant star system, but a rotating supermassive black hole, so immense that whole worlds can orbit close to it, and time can begin to separate into different human realities. Which means the next step is to ask whether Gargantua is the film's boldest fiction, or the place where its science becomes most impressive. Gargantua is where Interstellar stops asking for our curiosity and starts demanding our respect. Long before the story reaches its emotional extremes, This black hole has already done something rare in modern science fiction. It has convinced a mass audience to stare at a genuinely relativistic object and feel that the strangeness on screen belongs to the laws of nature rather than to visual fantasy. That achievement matters because black holes are often treated as dramatic shortcuts in storytelling. Here, the black hole is not decoration, it is the architecture of the entire system. To understand why that matters, we need to be clear about what Gargantua is meant to be. It is not an ordinary stellar black hole formed from the collapse of a massive star. Those are real, but they are much smaller. Gargantua is a supermassive black hole, the kind of object usually found in the centers of galaxies, with a mass millions or even billions of times greater than the Sun. The film needs such an enormous black hole for a very practical scientific reason. Near a small black hole, tidal forces become catastrophic very quickly. A person or spacecraft approaching too closely would be torn apart long before reaching the horizon. But for a supermassive black hole, the scale changes. The event horizon is so large that the gradient in gravity at the horizon can be much gentler. That does not make it safe. It simply makes certain close approaches less immediately impossible. That alone is one of the film's smartest choices. If Interstellar had centered its planetary system around a smaller black hole, much of what follows would have failed before it began. The crew would not have been skimming dramatic but survivable orbits near a horizon. They would have been entering a death zone with almost no room for narrative flexibility. By choosing a supermassive black hole, the film buys itself a narrow strip of plausibility. It is still an extraordinary environment, but not automatically a ridiculous one. Then there is the question of spin. Gargantua is not just massive, it is rotating rapidly, and that is essential. In general relativity, a spinning black hole is described differently from a non-rotating one. Rotation changes the surrounding space-time, it drags it, it twists it. It creates an effect often described as frame dragging, where space-time near the black hole is pulled around in the direction of the spin. This has enormous consequences for orbits, for the structure of the accretion disk, and for how close stable motion can occur without everything plunging inward. That last point is crucial. If Gargantua is spinning fast enough, the innermost stable orbits can sit closer to the black hole than they otherwise could. That means a planet might, in principle, orbit at an astonishingly close distance while still remaining outside the point of no return. Interstellar depends on this. The famous time dilation near Miller's planet only becomes remotely plausible if the planet is orbiting very deep in Gargantua's gravitational well, and that requires a rapidly spinning black hole. Without extreme rotation, the planet would have to stay farther out, and the entire timing of the film would weaken. This is where the science begins to feel almost surgical. The black hole is not simply large because large sounds impressive, it is large because only something supermassive softens the immediate tidal violence. It is spinning because only extreme spin brings the stable orbits inward enough to support the film's most dramatic relativistic claims. The object is designed not for spectacle first, but for the demands of the physics the story wants to use. And yet physics alone is not enough. The black hole also has to look right. Before Interstellar, most fictional black holes were shown as dark circles swallowing nearby stars, often with accretion disks treated as flat, glowing rings. That image was visually simple, but physically incomplete. Near a black hole, gravity bends light so strongly that the disk would not merely appear as a flat band slicing behind darkness. Light from material behind the black hole would curve around toward the viewer. The top and bottom of the disk would appear lifted and wrapped by lensing. The black hole would distort the visual field in a way that feels almost impossible until you understand that the impossible-looking image is exactly the point. Interstellar took that seriously. Its simulation work became famous for a reason. Instead of inventing a black hole by instinct, the production relied on relativistic calculations to determine how light from the disk should travel around Gargantua before reaching the camera. The result was an image that felt alien but coherent, a bright disk wrapped above and below a dark center, a shape that made the viewer feel that light itself had lost the right to move in straight lines. For many people, this was their first intuitive encounter with what gravitational lensing really means when pushed into an extreme regime. That visual achievement is not just a technical footnote, it tells us something important about the film's priorities. Interstellar wanted the audience to experience wonder through accurate distortion, not merely through scale, but through geometry. The black hole is impressive not just because it is huge, but because the screen lets you feel that the surrounding space-time has become active, curved, and visually unstable. The image teaches as it awes. Still, once we move from visual appearance to physical environment, the questions become harder. A black hole this dramatic is not sitting quietly in darkness. Gargantua is surrounded by an accretion disk, a structure formed by matter spiraling inward, heating as gravitational energy is converted into radiation. In real astrophysical systems, accretion disks can be ferociously bright. They can emit across a huge range of the spectrum, including dangerous high-energy radiation. If a planet were orbiting close to such a system, radiation could become a serious problem. Heat, ionizing particles, and extreme luminosity might make habitability far more difficult than the film openly acknowledges. This is one of the places where Interstellar begins to negotiate with reality, rather than submit to it entirely. For the planetary system around Gargantua to work as a setting for exploration, the accretion environment cannot be as destructive as many real disks might be. The disk must provide some illumination, enough perhaps to explain the eerie brightness on the nearby worlds, while not blasting them into sterility. That is a delicate balance. It is not obviously impossible, but it is highly dependent on the rate of matter falling inward, the thickness and temperature of the disk, and the larger history of the system. And that history is one of the most underappreciated questions in the whole film. Even if we grant that planets can orbit close to a rapidly spinning supermassive black hole, how did they get there? Black holes do not form planetary systems in the ordinary way stars do. A star is born from collapsing gas, surrounded by a disk from which planets may emerge over time. A black hole, especially a supermassive one, belongs to a much more violent and exotic evolutionary context. The worlds in Interstellar are not impossible to imagine, but their origin is far from obvious. Did they form from material in some kind of disk around Gargantua? Were they captured? Did they migrate inward? Each possibility opens a new set of astrophysical challenges. This is where the film's realism becomes selective. It is rigorous about the black hole's relativistic behavior. It is much less interested in giving a full formation history for the system surrounding it. That is understandable. A movie has limited time and different priorities. But scientifically, this is one of the soft spots. A stable orbit is not the same as a believable origin story. It is one thing to calculate where a planet could move. It is another to explain how such a planet could actually come to exist and remain there over cosmic timescales. Yet the distinction should not make us dismissive. In fact, it reveals why Interstellar is so interesting. The film is constantly balancing two kinds of plausibility. There is dynamical plausibility, meaning whether something could behave this way once it already exists. And there is historical plausibility, meaning whether nature could really build such a thing. Interstellar often performs impressively on the first category, while asking the audience to be generous on the second. Gargantua exemplifies that balance perfectly. Its orbits are treated with care. Its optical appearance is treated with exceptional care. But the larger astrophysical origin of its surrounding worlds is left hazier. There is also the question of warmth and light. If humanity is searching for habitable or near-habitable worlds in this system, where does their energy come from? A black hole itself does not shine in the ordinary sense. The event horizon emits no sunlight. What shines is the matter around it, especially in the accretion disk. That means any nearby planet would be living under a sky defined not by a central star, but by the glow of surrounding infall. The directionality of light, the rhythm of heating, and the climate consequences could all be deeply unusual. Day and night might not resemble anything Earth evolved under. Illumination could come from a smeared and distorted source, rather than a clean solar disk. That makes the worlds of Interstellar feel both more and less plausible at once. More plausible because the film recognizes that these planets are not simply substitute Earths with exotic scenery. Less plausible because the climate behaviour of such worlds would likely be very strange, perhaps harsher and harder to stabilise than the story can fully explore. But again, the film earns some credit simply by understanding that a black hole system changes the rules. These are not ordinary exoplanets in ordinary sunlight. They are worlds living in the shadow and glare of relativistic gravity. The name Gargantua itself is fitting, because scale solves some problems while creating others. A larger black hole weakens tidal gradients at the horizon, which helps. A rapid spin permits deeper, stable orbits, which helps. But to support nearby planets, survivable mission trajectories, dramatic lensing, and the enormous time dilation that later defines the story, Gargantua has to sit in a remarkably specific part of possibility space. Too small, and the tides kill you. Too slow, and the orbits sit too far out. Too bright, and radiation sterilizes the worlds. Too dim, and the system loses some of its visible logic. The black hole has to be not just supermassive, but almost narratively tuned. And yet tuned is not the same as false. That is the most important thing to recognize. Interstellar does not get away with nonsense here. It gets away with precision under constraint. It chooses the kind of black hole that gives its later scenes the best chance of surviving contact with actual physics. In a genre where black holes are often treated as magical sinkholes or glowing storm clouds, that alone is remarkable. But perhaps the most revealing sign of the film's seriousness is that Gargantua feels mysterious for the right reasons. Not because the audience is being asked to ignore science, but because the science itself is strange enough to create awe honestly. A rotating black hole really does drag space-time. Light really can bend into haunting arcs. Time really can separate between regions of different gravity. The film is not inventing the emotional power of these ideas. It is borrowing it from the universe. That brings us to the worlds orbiting Gargantua, where the balance between rigour and speculation becomes even more delicate. It is one thing to build a black hole that behaves in mathematically informed ways. It is another to place a planet impossibly close to it and claim that this world can endure the tides, the radiation, and the savage difference in time itself, which means the next question is no longer whether Gargantua is real enough, but whether Miller's planet has any right to exist where the film places it. Miller's planet is where Interstellar makes its most audacious scientific promise. Not because it places a world near a black hole, though that is already extreme, and not because it covers that world in tidal violence, though that too stretches the imagination. Its boldest claim is simpler and more disturbing. Spend a few hours on that surface, and decades pass elsewhere. A brief landing becomes a theft of human life on a scale that feels almost mythic. The film presents it as the cost of proximity to Gargantua, and unlike the wormhole or even the planetary arrangement itself, this idea begins with something undeniably real. Gravitational time dilation is not fiction. Time really does pass differently in different gravitational conditions. A clock closer to a massive object runs more slowly than a clock farther away. This is one of the direct consequences of general relativity, and it has been tested repeatedly. Even on Earth, the effect exists. A clock at sea level ticks slightly more slowly than one high above the surface, where gravity is marginally weaker. The difference is tiny, but measurable. Satellites in orbit must account for relativistic corrections because their clocks do not keep time in exactly the same way as clocks on the ground. Modern navigation systems would drift into error if relativity were ignored. That is the first important point. Interstellar did not invent the principle. It amplified a real effect into an extreme environment. The question then is whether the film amplifies it too far. On Miller's planet, roughly 1 hour corresponds to about 7 years farther away from Gargantua. That ratio is so enormous that it almost sounds symbolic rather than physical. Yet in principle, relativity does allow time to separate dramatically near very strong gravitational fields. The deeper you sit in a gravitational well, the more slowly your local clock runs relative to clocks higher up. Near a black hole, that effect can become extraordinary. But near is doing a tremendous amount of work in that sentence. To get time dilation this severe, Miller's planet cannot merely be orbiting a black hole in some broad outer zone. It has to sit in an exceptionally deep relativistic region, so close to Gargantua that tiny changes in radius would matter enormously. This is why the black hole's spin became so important in the earlier discussion. A rapidly spinning black hole allows stable orbits to exist closer in than a non-rotating one. Without that spin, the orbit required for such extreme time dilation would likely be unavailable to a planet that still hopes to avoid immediate destruction. Even with extreme spin, though, the configuration is delicate. The planet must orbit very near the innermost safe region, and the black hole must be massive enough that the tides at that distance are not instantly catastrophic. That combination is rare and demanding. It does not break relativity, but it forces the entire system into a narrow corridor of plausibility. Gargantua has to be almost maximally cooperative with the script. This is part of what makes Interstellar so fascinating scientifically. It does not land in a clean category of right or wrong. It operates in a regime where the underlying mechanism is absolutely real, while the exact numerical drama depends on extraordinary fine-tuning. The film is not lying about what gravity can do to time. It is asking the audience to accept a planetary orbit that extracts almost the most extreme useful version of that truth. And when you think about what that means for the characters, the physics becomes emotionally brutal. On Earth, or on the Endurance waiting higher in the system, time proceeds in one human rhythm. On Miller's planet, it proceeds in another. These are not just different clocks, they are different biographies. Every minute spent solving a practical problem on the surface becomes a surrender of years elsewhere. A delayed return is not an inconvenience. It is the irreversible loss of relationships, opportunities, and entire phases of life. Interstellar uses relativity not as abstract science, but as tragedy measured by clocks. That emotional clarity is one reason the scene works so powerfully. The idea is complicated, but the consequence is intimate. You do not need tensor equations to feel what it means to come back and discover that decades have passed for someone you love. The science becomes human through time itself, and in that respect, the film handles the concept beautifully. Still, the closer we examine Miller's planet as a physical world, the more unstable it begins to look. Time dilation is only one side of living so close to Gargantua. The other is gravity's uneven pull across the body of the planet. Tidal forces arise because gravity is stronger on the near side of an object than on the far side. On Earth, tides are familiar and relatively gentle because the gravitational differences across our planet are modest. Near a black hole, those differences can become enormous. Even around a supermassive black hole, where the event horizon itself may not be instantly lethal, any nearby world must still contend with severe tidal stresses depending on its orbital radius and the black hole's mass. This leads to a subtle but important distinction. Saying that a supermassive black hole has weaker tidal forces at the horizon than a smaller black hole does not mean that all nearby orbits are comfortable. It only means that the gradient can be less murderous at a given relative location. Miller's planet is not merely near Gargantua in some general sense. It is near enough to experience the extreme time dilation that drives the story. That makes tidal effects impossible to ignore. The film represents those tides through the giant waves that sweep across the shallow planetary ocean. These waves are some of the most memorable images in Interstellar, and they communicate something useful immediately. This is not a normal world. Its entire surface exists under the influence of a gravitational regime that has no earthly parallel. The ocean is not just weather, it is a visible expression of the planet's placement inside an extreme relativistic environment. But can tides alone really produce what the film shows? That is where things become harder to defend. Tidal forces can deform a world, especially if the body is fluid-rich and locked into a close gravitational relationship. They can create heating, flexing, and long-term geological consequences. In some systems, tidal stress may help sustain subsurface oceans or volcanic activity, but the specific image of towering wall-like waves endlessly racing across a nearly featureless shallow ocean is not a straightforward prediction of black hole physics. It is a dramatic interpretation of what severe tidal influence might feel like, not a clean simulation of what a stable ocean world under such forces would necessarily look like. A more realistic outcome might involve persistent deformation of the planet's shape, intense tidal locking, global stress patterns, or complex ocean bulges tied to orbital and rotational dynamics. The surface would likely be governed by a constant struggle between the planet's own gravity, the black hole's gradient, and the body's internal structure. Whether this would produce the exact cinematic waves of the film is doubtful. Those waves work as storytelling because they turn invisible gravity into visible danger. But scientifically, they probably belong more to imaginative translation than to precise expectation. There is also the issue of the planet's rotation and orientation. A world orbiting that close to a dominating mass would likely face strong pressure toward tidal locking, where the same side continually points toward the black hole, much as our moon keeps one face toward Earth. If Miller's planet is tidally locked or close to it, then the distribution of tides, illumination, and long-term environmental conditions becomes even more complicated. The black hole itself does not shine like a star, but the accretion disk does, and its apparent position in the sky would matter. So would the dynamics of the orbit. The world might not enjoy anything like ordinary day and night. Its surface environment could be governed by patterns far stranger than the film has time to explore. Then there is the planet's shape. Under very strong tidal forces, a body can be stretched. It may not remain comfortably spherical. Its internal structure matters here. A rigid, rocky planet resists deformation more than a fluid one, but resistance is not immunity. The closer the orbit, the greater the strain. There is a general limit in gravitational systems, often associated with tidal disruption, where an object held together by its own gravity can no longer remain intact if it gets too close to a much more massive body. Miller's planet presumably remains outside any immediate destruction threshold, but the margin may be uncomfortably small if we also demand the film's extreme time dilation. This is one of the recurring patterns in Interstellar. Each individual idea can be defended up to a point. Supermassive black hole? Plausible. Rapid spin? Plausible. Strong time dilation? Plausible. Tidal stress? Plausible. A nearby orbiting planet? Perhaps plausible. But when all of them are stacked together at their most dramatic values, the burden grows heavier. The film asks not for one extraordinary condition, but for many extraordinary conditions cooperating at once. That does not make the scene worthless as science. In some ways, it makes it more valuable. It gives the audience a vivid encounter with the genuine logic of relativity, and then invites them to ask where realism shades into cinematic compression. Miller's planet is not scientifically empty spectacle. It is a genuine thought experiment dramatized for emotional force. The black hole really can slow time. A nearby world really would face immense gravitational stress. The film simply turns those truths to their sharpest narrative angle. And there is something else worth noticing. The terror of Miller's planet is not based on monsters, combat, or chaos in the usual sense. It comes from clocks and geometry. The danger is not evil intent, it is misplaced scale. Humans enter a region where the universe is operating according to laws so far beyond ordinary experience that survival becomes partly a matter of whether your intuition can catch up before your lifespan is spent somewhere else. The wave is frightening not only because it is large, but because it arrives in a place where every delay has already become a wound in time. That may be why the planet remains so haunting, even if some of its details are arguable. It turns relativity into atmosphere. The whole world feels wrong in the way a truly alien environment should feel wrong. Empty horizon, shallow water, massive waves, a sky ruled by the presence of Gargantua, and beneath all of it, the sickening awareness that your local experience is no longer a trustworthy measure of reality for everyone else. When the crew leaves Miller's planet and discovers how much time has passed for Romilly, the science lands with devastating clarity. What had seemed like a difficult landing in bad conditions becomes one of the costliest decisions in the film. Not because anyone was foolish, but because the environment itself was running on a different temporal scale. This is where Interstellar proves that hard science ideas can carry emotional weight, usually reserved for more obviously dramatic devices. Time dilation is not a textbook aside. It is grief with equations behind it. And yet even here, where the film is at its most admired scientifically, we should be careful not to give it too easy a victory. Miller's planet probably pushes plausibility right to the edge. The time dilation is rooted in real relativity, but the exact magnitude and the stable existence of the planet in such a position demand an environment almost too convenient to be natural. The waves make the invisible visible, but they are likely more symbolic than predictive. The world works because the film understands the science deeply enough to dramatize its consequences, not because every feature is a strict astrophysical forecast. That distinction will matter even more as we move from the planet itself to the image of Gargantua that made all of this seem believable in the first place. Because one of the most remarkable things about Interstellar is that the science was not only written into the script, it was rendered into the light on screen. The black hole did not merely support the plot, it forced the filmmakers to confront what relativity would actually do to a viewer's eye, and what they discovered was so strange that even a science-conscious film had to decide how much truth an audience could comfortably look at. What the audience saw in Interstellar was not just a black hole designed to look impressive. It was the result of a serious attempt to let physics shape the image before art adjusted it. That order is rare. In many films, science is consulted after the visual has already been imagined, mainly to keep the fiction from drifting too far into absurdity. Interstellar reversed that process more than most people realized. It began with equations, followed the paths that light would actually take through warped space-time, and only then decided where cinematic readability had to take priority over literal realism. That approach matters because black holes are easy to misrepresent in ways that feel intuitive but are physically empty. A flat, glowing ring around a dark center looks neat. It also hides the true strangeness of the phenomenon. Near a rotating black hole, light does not travel in straightforward lines from source to observer. The space-time itself is so curved that photons emitted from matter behind the black hole can be bent around it and redirected toward the viewer. The result is an image that defies ordinary expectation. Parts of the accretion disk that should seem hidden can appear lifted above and below the black hole. Geometry begins to act like a lens made from gravity alone. To create Gargantua, the filmmakers worked with relativistic calculations that traced those light paths. Instead of painting a black hole with a ring for dramatic effect, they built a simulation that asked where the light from the disk would actually go. This is one of the reasons the final image became so iconic. It looked surprising for the right reason. The black hole did not seem alien because the artists were trying to be weird. It seemed alien because the laws of space-time really are weird at that scale. You can feel that in the shape of the image itself. The glowing disk appears both where you expect it and where you do not. It wraps over the top and under the bottom of the dark center, as if the black hole were somehow displaying different sides of the same structure at once. In ordinary Euclidean intuition, that feels wrong. In general relativity, it is exactly the kind of visual wrongness we should prepare for. The black hole is not revealing hidden surfaces by magic. It is forcing light to take paths that would be impossible in flat space. That makes Gargantua one of the most valuable visual explanations of gravitational lensing ever placed in a mainstream film. Lensing is often described in simple diagrams, where a massive object bends light from a background source, producing arcs or distorted images. But those diagrams do not fully capture what happens when the lens itself is extreme and the light source is wrapped intimately around it. Interstellar gave millions of viewers an intuitive glimpse of that regime. It turned abstract curvature into something you could feel with your eyes. Yet even here, where the film followed physics with remarkable seriousness, it still had to compromise. One of the major issues was brightness. In a strictly relativistic rendering, parts of the accretion disk moving toward the observer at enormous speed would appear much brighter than the receding side. This is a consequence of relativistic beaming and frequency shifting. Light from material racing toward you is compressed and intensified. Light from material moving away is stretched and dimmed. In a realistic image, one side of the disk could have looked dramatically more luminous than the other, producing a much harsher asymmetry. Scientifically, that would have been powerful. Cinematically, it risked confusing the audience. The shape of the black hole might have become harder to read. Instead of seeing a coherent object, viewers might have seen a strange lopsided blaze that obscured the very geometry the film wanted to communicate. So the image was softened. The brightness differences were reduced. The final result preserved the basic relativistic structure while making the object more legible to a non-specialist audience. This is an important distinction because it shows how Interstellar negotiated with truth rather than abandoning it. The filmmakers did not say, "Physics is inconvenient, let's ignore it." They said, "Physics is producing something so visually extreme that the audience may not understand what they are seeing unless we simplify certain features." That is not pure accuracy, but it is still a science-driven decision. The compromise exists in order to communicate the deeper reality more clearly. Colour posed a similar challenge. A real accretion disk around a supermassive black hole could emit across many wavelengths, including radiation well outside the visible range. Depending on temperature and composition, some of the most intense emission might not resemble the warm, cinematic glow audiences associate with fire or plasma. It might be harsher, stranger, or dominated by frequencies invisible to the eye. Once again, the film had to translate physics into human perception. The disc needed to feel astrophysical, but also readable as luminous matter in motion around an abyss. This is where cinema and science always meet on uneasy terms. The universe does not care whether its most extreme objects are easy to interpret. A film does. The audience has to understand what matters in a fraction of a second. So every image in a science film exists somewhere between strict physical output and perceptual storytelling. Interstellar deserves credit because it kept that distance narrower than most. The same applies to the wormhole. Although Gargantua became the more famous image, the wormhole visuals were shaped by the same underlying respect for curved space-time. A wormhole should not look like a flat cutout hanging in space. It should redirect light from the region behind and around it in ways that make local geometry feel unreliable. The film again resisted the easy cliché. It tried to imagine what such a structure would actually do to the surrounding starfield. That visual discipline helps explain why the wormhole and the black hole both feel weighty rather than decorative. They are not just dramatic locations, they are optical consequences of geometry. There is a deeper lesson in all of this. Interstellar is often praised for its scientific ambition, but the most impressive part is not simply that it consulted a physicist or included real concepts in the dialogue. Many films do that superficially. What sets this one apart is that it allowed science to constrain the image-making process itself. The camera, in a sense, had to obey relativity. That is a far more difficult kind of respect. It means the film did not merely want to talk about black holes. It wanted to ask what black holes do to seeing. And once you ask that question honestly, another one follows. What are audiences actually prepared to see? Scientific truth at the edge of comprehension often looks less elegant than fiction trained us to expect. It can be asymmetrical, overwhelming, optically confusing, and almost hostile to ordinary intuition. A perfectly faithful rendering might have been more accurate, but less useful as storytelling. So the film stood at a crossroads familiar to all science communication. Preserve every difficult detail, or simplify in order to preserve understanding. Interstellar chose selective simplification. That was probably the right choice for a movie, but it is worth appreciating exactly what was lost and what was preserved. Lost were some of the harsher brightness asymmetries, and perhaps some of the more bewildering visual consequences of extreme relativity. Preserved were the essential facts that the black hole bends light profoundly, that the accretion disk does not look flat when space-time is curved this severely, and that the object's visual strangeness is not fantasy dressing. It is the outward sign of real geometry. This makes Gargantua more than a successful effect. It becomes a case study in how scientific realism survives translation into mass culture. The film did not keep every detail intact, but it kept the logic intact. It respected the reason the image should look strange, and because of that, the audience was invited into a more honest kind of wonder. Not wonder at whatever the artists could invent, but wonder at what the universe already permits. It is also worth noting that the visual simulation work around Gargantua had consequences beyond cinema. When artists and scientists collaborate seriously on a relativistic rendering problem, the The process can sharpen intuition in both directions. Scientists gain new ways of communicating curvature and light paths. Artists discover that the universe can generate images more surprising than many fantasies. In that exchange, the film becomes more than entertainment. It becomes a bridge between technical knowledge and public imagination. That bridge matters because so much of black hole science is invisible by default. We cannot simply fly a camera to an event horizon and watch what happens. Even the real black hole images produced by astronomy are not photographs in the ordinary sense. They are reconstructions based on signals, inference, and careful processing. The public understanding of black holes is therefore always mediated through models, visualizations, and conceptual translations. Interstellar entered that space with unusual responsibility. It helped teach people that a black hole's appearance is shaped not just by darkness, but by the violent bending of light itself. And yet there is an irony here. The more believable Gargantua becomes visually, the more pressure falls on the worlds around it to withstand scientific scrutiny. A convincing black hole does not automatically guarantee convincing planets. In fact, it raises the stakes. Once the audience senses that the film has respected relativity in the image, they become more willing to trust the larger system. That trust is powerful, but it can also hide the places where realism becomes thinner. We have already seen that Miller's planet lives at the edge of what the film can plausibly defend. Man's planet and Edmund's planet will test that edge in different ways. One is presented as a frozen disappointment, almost a scientific fraud embodied as a landscape. The other lingers as the one remaining hope, a world the film wants us to believe might truly sustain life. But once these planets are judged not just as dramatic backdrops, but as astrophysical objects in a black hole system, very different questions begin to emerge. The problem is no longer only what they look like, it is whether their atmospheres, surfaces, and climates make sense at all, especially when one of them appears built from conditions that are far harder to justify than the film initially lets on. What makes Man's Planet so effective in the film is that it feels like the collapse of confidence made physical. After the precision of Gargantua and the terrible clarity of Miller's planet, Man's world arrives as a frozen blank, pale, silent, and seemingly solid enough to promise refuge. The story needs that false promise. Humanity's survival cannot depend only on spectacular danger. It also depends on misjudgment, incomplete data, and the desperate tendency to believe in a livable world because the alternative is unbearable. But once we begin asking scientific questions again, Man's Planet becomes much harder to defend than the film's earlier environments. On screen, the world appears as a vast field of ice and cloud, with a surface that can support landing and movement while concealing a deeper instability. The atmosphere is thin and toxic. The horizon is cold and muted. Everything about the place communicates disappointment. It is a planet that looked hopeful from afar and failed when tested more closely. That emotional function is clear. The harder question is what kind of world could actually behave the way the film wants this one to behave. The first issue is the frozen cloudscape itself. The film suggests a world where enormous frozen formations rise above a deep atmospheric layer, almost like suspended mountains of ice. Visually, it is one of the more haunting settings in Interstellar, but physically, it is difficult to interpret. Clouds do not simply become landforms because a planet is cold. Their structure depends on atmospheric composition, pressure, temperature gradients, convection, and condensation behavior. A truly frigid atmosphere can certainly support clouds made of substances other than water, and planets or moons in our own solar system already show us that weather can be very alien. But the precise structures on Man's planet occupy a strange middle ground between cloud, glacier, and terrain. This matters because cloud physics is unforgiving. If the formations are clouds, then they are dynamic atmospheric structures, not stable ground in the ordinary sense. If they are solid deposits, then they need a convincing process of accumulation, support, and persistence. The film wants both impressions at once. It wants the world to look like a planet made of frozen atmosphere, while still providing surfaces the characters can move across. That is a strong visual metaphor, but it does not map neatly onto a well-defined planetary environment. The atmosphere itself raises another problem. Man's world is presented as oxygen poor and unsuitable for humans, which is entirely plausible. Most planets would be. But the surrounding conditions matter. If this is a cold, hostile world in orbit within Gargantua's broader system, then its temperature, atmospheric stability, and surface structure all depend on where it sits relative to whatever energy sources the system provides. Unlike a normal planetary system with a central star, this is a black hole-dominated environment, which means illumination and heating are already unusual. If man's planet lies farther from Gargantua, or from the effective radiative influence of the accretion disk, then deep cold becomes easier to imagine. But once the film wants thick atmospheric behavior, frozen cloud architecture, and landing conditions that are precarious rather than instantly unsurvivable, the details begin to pile up. There is also the issue of long-term stability. A planet is not interesting scientifically just because it can momentarily look dramatic. It has to make sense as an object that has existed for some span of time. Can a world with these atmospheric properties retain its gases? Can it maintain the temperature structure needed for the cloud layers the film implies? Can its surface environment remain coherent under the larger gravitational context of Gargantua's system? These are not easy questions, and the film does not really try to answer them. Unlike Gargantua itself, which was built with relativity in mind, man's planet feels much more like a dramatic environment, shaped first by theme and second by science. That is not necessarily a flaw in a storytelling sense. In fact, it suits the planet's role. Man's world is meant to be deceptive. It is the physical embodiment of false data, false hope, and moral collapse. It does not need the austere conceptual elegance of Miller's planet. It needs to feel unstable, uncertain, and wrong. The problem is that once you ask whether the world is astrophysically convincing, the answer becomes far shakier. It is not pure nonsense, but it is clearly less rigorous than the black hole and less anchored than the time dilation sequence that made the earlier part of the film so famous. This contrast is revealing. It shows where Interstellar is most disciplined and where it becomes more permissive. When the science is central to the film's identity, wormholes, time dilation, black hole optics, the screenplay and visual design work very hard to stay near serious physics. When the science mainly supports a psychological or moral beat, the film is more willing to blur the edges. Man's Planet is one of those blurred edges. It functions powerfully as drama, but it asks for more generosity as science. That generosity becomes even more obvious when we consider Dr. Mann himself. His deception is not just a character twist, it is also a statement about the difficulty of interpreting remote planetary data. In real planetary science, especially for exoplanets, habitability is never established from one clean signal. We infer, we compare spectra, we estimate temperatures, atmospheric composition, orbital distance, density, and stellar environment. Each clue matters, and each can mislead when the data are incomplete or noisy. In that sense, the film touches a genuine scientific vulnerability. Worlds seen from afar can appear more promising than they really are. The line between a tantalizing candidate and a dead end can be very thin. That makes Edmund's planet all the more important. If man's world is the lie, then Edmund's world is the possibility that still remains once deception has been stripped away. The film offers it less screen time, but in some ways it carries the largest scientific burden of all. Miller's planet is too extreme. Man's planet is false. Edmund's planet must be the world that can plausibly bear the weight of human future. It has to feel less like a thought experiment and more like a destination. What would that require? At minimum, a genuinely habitable world needs a relatively stable environment where liquid water can exist over meaningful timescales, where radiation is not catastrophically destructive, where atmospheric pressure and composition are compatible with long-term survival, or at least adaptation, and where the planet's orbit does not subject it to relentless environmental chaos. In ordinary exoplanet science, these criteria are already difficult enough. Around Gargantua, they become stranger still. A habitable world in this system would not simply need the right distance from a sun-like star. It would need the right relationship to the energy emerging from its environment, whether from a local star, if one exists in the wider system, from accretion-related radiation, or from some more complicated configuration the film leaves mostly unspoken. That is one reason Edmund's Planet remains more atmospheric suggestion than detailed model. The film wants us to accept that one of the candidate worlds is good enough to try. It does not want to linger on the full astrophysical accounting that such a claim would require. Even so, Edmund's Planet is easier to believe in than the other two for a simple reason. It appears less extreme. It does not demand vast time dilation. It does not rely on impossible-looking frozen cloud continents. It seems, at least by comparison, more Earth-like in its basic promise. And in scientific storytelling, moderation often helps plausibility. A world that asks less from the laws of nature is usually easier to defend than one built from stacked exceptions. That does not mean it becomes automatically realistic. We still have to ask where the world gets its energy, how its atmosphere evolved, what its long-term orbital history looks like, and whether the wider black hole environment would allow the sort of stable biosphere the film hopes for. But because Edmund's Planet is not presented as a showpiece of extreme relativity or bizarre meteorology, the audience is more inclined to grant it the benefit of the doubt. It feels like the least extravagant claim in the system, and therefore the most believable. There is a larger lesson hiding inside this contrast between the three worlds. In astronomy, habitability is not a single property. It is an accumulation of tolerances. A planet does not become livable because one measurement looks promising. It becomes livable because many conditions, some obvious and some subtle, all fall into a survivable range at the same time. Temperature, atmosphere, chemistry, radiation, orbital stability, geology, magnetic environment, and long-term climatic behavior all matter. Miller's planet fails because time and tides dominate everything. Man's planet fails because appearance and data mislead. Edmund's Planet survives, at least narratively, because it represents the one case where enough of those tolerances may align. That makes the progression through these worlds feel more than arbitrary. It is almost a compressed drama about exoplanet optimism itself. First, the extraordinary world that seems scientifically glorious but humanly punishing. Then the fraudulent world that embodies the fear of being fooled by our own hope. Then the quieter world that may actually work, not because it dazzles us most, but because it demands the least suspension of environmental realism. In that sense, Interstellar accidentally mirrors a truth of planetary science. The most dramatic worlds are not always the most habitable. Sometimes the real prize is the one that appears less spectacular and more stable. Still, even if Edmund's Planet is the easiest of the three to accept, the film never truly settles its science. It leaves the world as an open destination rather than a deeply examined environment. That is probably wise. The closer Interstellar gets to concrete planetary details, the more vulnerable it becomes to scrutiny. Its greatest strength lies in the large-scale physics around black holes and time, not in exhaustive climate modelling. By keeping Edmund's Planet mostly ahead of us, the film preserves its symbolic power as a destination of possibility. And that symbolism matters, because by this point, the story is no longer driven only by astrophysical curiosity. It is driven by narrowing options. Humanity has crossed a wormhole that may violate causality, orbited a black hole tuned to the edge of plausibility, lost decades to gravity on Miller's Planet, and nearly died on a frozen lie. Hope is no longer abstract. It has become local, fragile, and frighteningly specific. There may be only one world left worth trusting. That shrinking horizon sets up the film's most dangerous turn, because once man's deception has forced Cooper into direct confrontation with survival near Gargantua, the story can no longer stay at the level of maybe habitable planets and remote speculation. It moves instead toward the black hole itself. And the closer the film gets to the event horizon, the less room there is for atmospheric generosity. A fall toward a supermassive black hole is not just another dramatic setting. It is a direct test of whether the movie can keep carrying real physics all the way to the brink, or whether, at last, the narrative must ask science to step aside for something stranger. Science can follow Interstellar a surprisingly long way toward that brink. It can even follow Cooper farther than many viewers might expect. But once a human body begins falling in earnest toward a black hole like Gargantua, the room for narrative generosity starts shrinking fast. The first thing to understand is that falling into a supermassive black hole is not identical to falling into a smaller one. This matters enormously. In popular explanations, black holes are often associated with immediate spaghettification, the stretching of an object into a long, thin strand by tidal forces so severe that the difference in gravity between head and feet becomes fatal. That image is not wrong, it is just incomplete. The severity of tidal forces at the event horizon depends strongly on the mass of the black hole. For a smaller, stellar black hole, the gradient in gravity near the horizon can be catastrophic. For a supermassive black hole, the horizon is so much larger that the tidal gradient there may be far gentler. That means the horizon of Gargantua is not necessarily the instant death line that fiction often imagines. A spacecraft, and in principle even a person, could cross the event horizon of a sufficiently massive black hole without being torn apart at that exact boundary. This is one of the reasons Interstellar chose Gargantua so carefully. The film needed a black hole large enough that Cooper's plunge would not become physically absurd the moment it began. In that narrow sense, the movie earns another measure of plausibility. It understands that not all black holes kill in the same way, or on the same scale. But this is only a partial reprieve. Surviving the horizon is not the same as surviving the environment around it. Long before Cooper crosses into the black hole, he must pass through the region dominated by the accretion disk and by some of the most hostile radiation conditions in the entire system. Matter spiraling inward toward a black hole does not simply vanish quietly. It heats through friction, compression, and gravitational energy release. Depending on the structure of the disk, this can create intense radiation across a wide range of wavelengths. Even if Gargantua's disk is assumed to be thinner and cooler than the most violently feeding black holes, as the film's scientific defense often suggests, the environment is still deeply hazardous. Light, heat, and energetic particles do not become harmless just because the system is arranged to favor dramatic visuals over apocalyptic brightness. This is one of the most overlooked problems in the film. The black hole itself may allow close approach without instant tidal death, but the surrounding disk remains a serious threat. A spacecraft maneuvering near that region would not merely be solving an orbital problem, it would be confronting thermal stress, radiation exposure, and an environment where every trajectory brushes against matter and energy, falling into one of the most extreme objects in the universe. Interstellar keeps this danger in the background because the emotional focus is on sacrifice and descent. But scientifically, the disk may be as frightening as the horizon itself. There is another subtle issue here, one that reveals how strange black hole optics become at close range. Around a black hole there exists a region where light can orbit temporarily, trapped on precarious paths by gravity. Photons can circle before escaping, or before plunging inward. In practice, this means the visual environment near a black hole is not merely dark and curved, but layered with light paths that may loop, amplify, or build complex structures around the object. For an infalling observer, the sky would become increasingly distorted. The black hole would not simply grow larger in front of you like a dark hole in a wall. The surrounding universe would warp around it in ever more unnatural ways. That optical distortion is not just aesthetically interesting. It speaks to how little ordinary intuition can help once the fall truly begins. Directions stop behaving cleanly. The contrast between what the external universe is doing and what the infalling traveller experiences becomes more dramatic. To a distant observer, Cooper never appears to cross the event horizon in the ordinary sense. His image would seem to slow, dim, and redden, fading as light from him takes longer and longer to escape. From far away, he appears to freeze near the edge and disappear into darkness. But for Cooper himself, assuming nothing destroys him beforehand, there is no such freeze. He crosses the horizon in finite proper time. The event happens. The drama of black holes lies partly in this split between perspectives. The outside universe and the falling traveller do not agree on how the approach should look. This is one of the deepest truths Interstellar borrows from relativity. Different observers genuinely inhabit different descriptions of the same event, and both can be valid within their own frames. The film does not stop to teach that in a formal way, but its emotional logic depends on it. Cooper's descent is not just a plunge through space, it is a divergence in what time and observation mean for different people. To those outside, he is being lost to a boundary no signal can cross. To him, at least for a while, the experience continues. Yet continuation is not safety. Even around a supermassive black hole, the inward fall eventually becomes lethal. Tidal forces increase as the radius shrinks. The fact that they are manageable at or near the horizon does not mean they remain so indefinitely. Farther inside, the gradient worsens. Body, spacecraft, and structure all begin to suffer the same underlying fate. Gravity pulls more strongly on the nearer parts than the farther parts, stretching the infalling object along one axis and compressing it along another. Spaghettification is simply the memorable name for this geometric cruelty. The black hole does not tear you apart because it is hungry in some metaphorical sense. It tears you apart because space-time curvature stops treating your body as small. That line matters. In ordinary environments, we can ignore the fact that our body occupies a range of positions in a gravitational field. Earth's gravity does not differ enough between your head and your feet to matter biologically in any dramatic way. Near a black hole, that approximation fails. The field is not effectively constant over the length of your body, or your spacecraft, or your orbit. Curvature becomes personal, and once it does, the distinction between trajectory and destruction disappears. So could Cooper survive for any meaningful time after crossing Gargantua's horizon? Not in the way the film finally requires. A supermassive black hole gives the story some breathing room, yes. It may delay the worst tidal effects. It may allow passage through the horizon without immediate disintegration. But surviving deep enough, long enough, and coherently enough to reach some usable interior structure is another matter entirely. That is where the film begins departing much more decisively from scientific expectation. There is also the problem of communication. Outside the event horizon, signals can still in principle escape, though increasingly redshifted and delayed. Once inside, ordinary communication outward is over. That is not a practical limitation. It is built into the causal structure of the black hole. The event horizon is not simply a dangerous region. It is the boundary beyond which future directed paths no longer lead back out. You do not fail to send a message because your equipment breaks. You fail because the geometry of space-time itself no longer offers a route for that message to reach the outside universe. This makes the black hole's horizon one of the cleanest dividing lines in physics. Before it, escape may be difficult. After it, escape is not part of the future. That is why so much of the later film becomes controversial. The closer Interstellar stays to the approach, the stronger its scientific footing remains. Once it starts asking what can happen after the horizon in a way that affects the exterior world, it is moving on to much thinner ice. Still, the approach itself deserves credit for how much truth it contains. A black hole does distort time and observation. A supermassive horizon can be less immediately violent than many people assume. An outside observer and an infalling observer do describe the fall differently. Accretion disks and lensing do create a perilous and optically bizarre environment. These are not fake ideas. They are some of the most remarkable genuine consequences of general relativity. Interstellar carries them impressively far into mainstream storytelling. And that is precisely why the remaining departure matters so much. The film earns the audience's trust with real physics, then spends that trust at the most dramatic possible moment. As Cooper falls inward, the black hole begins to stop functioning as an astrophysical object alone and starts becoming a threshold between two genres. On one side is hard science, stretched but recognizable. On the other is the film's final wager, that the interior of this collapse can somehow be transformed into a place where information, gravity, memory, and time remain available to human action. The closer Cooper gets to that wager, the more the earlier scientific discipline matters. Without the realism of the fall, the leap beyond it would feel cheap. With that realism, the leap feels almost earned, even when physics itself is no longer really following along. That is the strange achievement of this descent. It is persuasive right up to the moment it should stop being possible. Cooper's sacrifice works emotionally because the black hole has already been built as something more than fantasy. We have seen the lensing. We have accepted the time dilation. We have watched entire lives be lost to gravity's arithmetic. So when he drops away from the endurance and commits himself to Gargantua, the scene carries the force of genuine science turning into genuine doom. For a moment, the film seems ready to let the universe be as merciless as relativity says it is. And if it had stopped there, at the level of the fall alone, Interstellar might have remained one of the most scientifically disciplined black hole sequences in cinema. But it does not stop there. It keeps going. It turns the interior of the black hole into the doorway for its most ambitious and least defensible idea. Because once Cooper is no longer merely falling toward an event horizon, but arriving somewhere beyond it, the question changes completely. We are no longer asking what a supermassive black hole does to a body or a signal. We are asking whether space-time itself can be opened from the inside into something like a higher dimensional archive, a place where the past is laid out like a landscape, gravity becomes a language, and the entire story folds back on itself. That is the point where Interstellar stops asking what current physics can describe with confidence and starts asking what current physics might inspire if pushed into metaphor, higher dimensions, and causality loops. The black hole is no longer just a gravitational object. It becomes the staging ground for the film's final transformation of scientific language into emotional architecture. The Tesseract is the clearest example of that transformation. In the film, Cooper does not simply die inside Gargantua or vanish into unknowable singularity. He arrives in a constructed higher dimensional space that allows him to perceive different moments in Murph's room as if time were laid out spatially. The image is powerful because it takes something human beings never experience, the idea that time might be seen all at once from outside its ordinary flow, and turns it into a visual environment. Memory becomes geometry, duration becomes location. A room stops being a place and becomes a web of moments. To understand why this is such a striking leap, it helps to separate the elements. A tesseract in mathematics is a higher dimensional analogue of a cube. That idea, by itself, is not mystical. Mathematics routinely studies spaces with more dimensions than the three of ordinary geometry. Physics also makes use of higher dimensional frameworks in various speculative theories, so the film is not inventing the language of higher dimensionality from nothing. What it is doing is translating that language into a narrative claim. If beings with access to higher dimensions existed, perhaps they could perceive time differently from us, and perhaps what we experience as a sequence would look to them more like a structure. That is imaginative. It is also where the film steps decisively beyond established science. Current physics does not give us evidence that humans falling into black holes encounter navigable higher dimensional libraries of their own past. Nor does it give us a mechanism by which a person inside an event horizon could interact selectively with moments in another person's room while preserving the larger causal history of the universe. These ideas borrow vocabulary from relativity, geometry, and speculative dimensional thinking, but they do not emerge as a known consequence of black hole interiors. They are extrapolation shaped by story. Still, the extrapolation is not random. It grows from a real tension already present in the movie. Throughout Interstellar, time has been treated not as a fixed universal river, but as something that stretches, separates, and depends on geometry. The Tesseract radicalizes that theme. If time can dilate, if different observers can disagree about its passage, if the structure of space-time can become deeply non-intuitive near black holes, then the film asks whether time could be treated as an accessible dimension under even stranger conditions. That is not a scientifically justified conclusion, but it is a narratively coherent escalation of the film's deepest obsession. The next question is gravity, because the film chooses gravity as the one force capable of crossing the divide between Cooper's impossible position and Murph's world. This is a clever choice for a specific reason. Gravity already occupies a special role in general relativity. It is not just a force moving through space, it is bound up with space-time itself, and unlike light trying to escape from within the horizon, the film suggests that gravitational influence can still be part of the larger structure, tying the inside and outside together. In dramatic terms, this allows Cooper to communicate not with words or radio, but with physical nudges in the world Murph can observe. Scientifically, this is where the story becomes far more conjectural than the earlier black hole material. The idea that useful information could be encoded through gravity from beyond the horizon and delivered in a way that preserves the external plot is not supported by known physics. The horizon remains a causal barrier. The movie's solution is not really a hard science solution. It is a science-flavoured narrative bridge. By choosing gravity, however, the film gives itself the most elegant possible version of that bridge. It avoids raw magic by using the one phenomenon already central to everything the film has been exploring. That matters because the ending is trying to do two things at once. It wants emotional closure, and it wants closure that feels consistent with the scientific atmosphere the movie has worked so hard to build. A purely supernatural ending would have broken the tone. A purely scientific ending would likely have been much colder and harsher. The Tesseract and the gravitational communication thread the needle. They are not scientifically credible in a strict sense, but they are aesthetically credible within the film's own framework. They feel like a continuation of the same universe, just after that universe has crossed from demonstrated physics into speculation. Then comes the bootstrap paradox, which may be the most quietly radical idea in the entire film. Cooper uses the Tesseract to help Murph solve the gravitational problem that allows humanity's survival. But the means by which he does so depend on events that only happen because humanity survives long enough to create, or somehow enable, the higher dimensional intervention in the first place. Cause and effect begin feeding each other in a loop. The future saves the past, so that the past can produce the future that performs the saving. This kind of loop is fascinating because it feels self-contained, almost elegant, until you ask where the information truly originates. Murph's breakthrough depends on data. Cooper sends that data, but Cooper can only send it because the chain of events created the conditions for him to occupy the Tesseract. The loop closes beautifully. It also erases any clean external origin for the crucial intervention. The information exists because it already exists in the loop. Physics does not currently give us a settled framework in which such bootstrap loops are understood as normal features of reality. They live in the same broad region of discomfort as earlier wormhole time travel paradoxes. Perhaps consistency could, in principle, allow them without contradiction. Perhaps the universe forbids them. What matters here is that Interstellar has been building toward this all along. The wormhole near Saturn was already a hint that the story might be living inside a causal structure stranger than linear survival drama. The Tesseract ending simply reveals that the whole narrative may have been loop-shaped from the beginning. That revelation changes how we understand the film's opening mystery. Humanity did not simply discover a wormhole and respond heroically. Humanity encountered a path that had, in some sense, already been prepared by its own future. This transforms the tone of the movie's science. What first looked like exploration begins to resemble a guided self-rescue threaded through time. That is dramatically satisfying, but it moves the story away from ordinary scientific uncertainty and toward a universe where history is partially self-authored. There is a philosophical cost to that move. In a bootstrap structure, agency becomes complicated. Did Cooper choose, or did he fulfill? Did Murph discover, or did she decode what was already embedded in the architecture of events? Some viewers find this beautiful because it suggests love, loyalty, and intellect can echo across time. Others find it unsettling because it narrows freedom into consistency. The future does not merely influence the past, it may already have determined the shape of the past that produced it. That tension is one reason the ending remains so memorable. It is not just science fiction spectacle, it is a confrontation between two human desires that do not fit together easily. We want the universe to be lawful, intelligible, and ordered, but we also want it to leave room for meaning, sacrifice, and return. Interstellar spends most of its running time earning the first desire through real scientific seriousness, then spends the ending satisfying the second through a speculative leap the science alone could never guarantee. And yet it would be unfair to say the film simply abandons science at the end. What it really does is carry science to the edge of what it can emotionally support, then step beyond it with unusual discipline. The leap into the Tesseract is not arbitrary fantasy pasted on top of a hard science movie. It is the culmination of themes the film has been developing consistently. Time as geometry, gravity as messenger, causality under strain, and the possibility that dimensions beyond ordinary perception could reframe what human beings call impossible. None of that makes the ending physically established, but it does make it artistically coherent. This is perhaps the fairest way to judge Interstellar as science fiction. It is not a perfect map of known astrophysics. It never was. Some of its planetary environments are highly debatable. Its wormhole depends on enormous theoretical generosity. Its black hole approach is strong until it reaches a region where known causal structure should close the door. Its ending rests on speculative, higher dimensional intervention and a bootstrap paradox with no secure physical basis. But it also does something rare. It refuses to trivialize the science it is borrowing. Even when it bends away from strict realism, it does so with reverence for the ideas themselves. That reverence is why the film continues to matter. It treats black holes, relativity, and higher dimensional thought not as decorative jargon, but as sources of genuine awe. It assumes the universe is already astonishing enough, that fiction does not need to replace science with nonsense. It only needs to know where science ends and where metaphor may begin. Interstellar crosses that border very late, and only after extracting extraordinary emotional power from the real physics on the near side of it. In the end, the film's greatest success may be that it leaves both responses alive at once. You can admire how carefully it rendered Gargantua, how seriously it handled time dilation, and how thoughtfully it built its central wormhole around real theoretical discussions. You can also recognize that the tesseract and the causal loop belong less to established science than to a beautiful act of speculative storytelling. Those two truths do not cancel each other. They define the movie. Interstellar remains compelling because it understands that science and wonder are not enemies. Science gives the wonder its weight. Wonder gives the science its human urgency. The film carries real relativity astonishingly far, then knowingly steps beyond it where equations no longer offer firm ground. It does not pretend that the final step is proven. It asks whether, at the edge of what physics can currently describe, the language of higher dimensions, gravity and time, might still help us imagine a story about survival, love, and causality that folds back on itself like space-time under impossible stress. And that is why the movie still lingers after the credits. Not because it solved black holes, wormholes, or time itself, but because it understood something just as important. The universe is strange enough to justify our deepest curiosity, and sometimes the boundary between disciplined science and disciplined imagination is where the most haunting stories are born.